All right, hi everybody. So the three questions that were most requested were numbers 9, numbers 11, and number 12. And so I'm going to make an effort to make a video to go through all of those three. I'm going to start with number 9, and I will also be posting the answer key to number 10 later on in the week. If there's any other problem that comes before number 9 you were really stuck on, you really need help with, please do try to see me during office hours or during class this week after we've discussed and dismissed. Okay. All right. So first off, number 9 asks about a child in a wagon. Whoa. So here's our wagon. Here's our little person. And he's sitting there while he's being pushed. And when it comes down to it, the pushes are the thing that we really care about. So we've got one child pushing on the wagon in one direction with a force of, let's call this guy 45 newtons. And then the child number 2 is pushing opposite of child number 1 with a force of 90 newtons. Then we have a friction force, which would oppose motion. We're going to talk about where to put that on this diagram, of 12 newtons. Mass of the third child plus the wagon is 23 kilograms. So we were given mass. And it says, in this first one, it says, what is the system of interest of this particular, if the acceleration is the thing that we're going to calculate? And the answer is the child plus the wagon. Okay. The second says to draw a free body diagram including all forces acting on the system. So again, when we do that, we draw our point. We draw forces that are acting on the system. Weight and normal are always in the diagram. We've got one child pushing to the right. So that's child 1's force of 45 newtons. We've got child 2's force, which is going to be bigger, 90 newtons. Since this child is moving with double the force, it means the wagon itself will actually move to the left. So that means we're going to put friction pointing opposite of the movement. Okay. And so when it comes down to it, you need to make sure you're understanding what's happening in this particular system before you can draw a free body diagram. And it did tell you that friction opposes motion. The big takeaway here is whatever the net force is the direction of motion. And it's going to be the thing with the largest force. So in our case, to the left is going to be the motion, which means friction has to go the other direction. Okay. Next thing that we're going to do is calculate the acceleration. Remember that weight equals mass times gravity if we need it. Normal opposes weight in this particular case. Don't think that really matters, but we do want to find F equals ma. In order to do this particular problem, we need to calculate F net. We know that 90 is going the opposite direction. So 90 gets a negative sign. Then we're going to add the two forces that are pointing to the right to get our net force is equal to, hold please, gotta get me a calculator. Oops. Negative 33 newtons From there, we're going to use that negative 33 newtons, set it equal to the 23 kilograms times the A we don't know, and we're going to get a negative 1.43 meters per second squared as the acceleration. Okay. The next problem asks what happens if friction is 15. So instead, our F net becomes negative 30, and we know that F net equals MA. So negative 30 equals the 23 kilograms still, because it doesn't say the system changes its mass or anything. And this time the acceleration gets slower. You get that. Okay. All right. Number 11 says that the weight of an astronaut plus his spacesuit on the moon is only 250 newtons. And remember, weight equals mass times gravity. And so if weight is 250 newtons times gravity, how much does this person in particular weigh on Earth? And now, here's our big question. What is the gravity of the moon? So in order to do this problem, you would have had to go back to your reading and find the fact that the gravity of the moon is approximately 1/6 that of the gravity of the Earth. So you would take your 9.81 divided by 6, and you get 1.63 meters per second squared equals the moon's gravitational constant. And so that's what we're going to plug in up here. Into our problem to solve for the mass, because once we know what the mass is on the moon, we can figure out what the weight is on Earth, because we know that the gravity of the Earth is always 9.81 meters per second squared. Okay, but if you missed this part in your reading, that's probably why you guys were a little bit confused. All right, so then I calculated the mass to be 152.9 kilograms based on this information. From there, I'm going to take that mass and I'm going to plug it into the weight vector equals mass times what? I apologize. I don't know why I did that. We're going to do weight equals mass times gravity, this time on the Earth, because we're trying to figure out what the weight on the Earth is. Okay, so his mass is 152.9 kilograms on the moon. One thing to remember is that mass is the thing that's constant no matter what. So when we say that something has a mass, that mass should be the same no matter where we are. So we're going to use that mass in our other calculation for the weight on the Earth. Times the gravitational constant on the Earth to get 1,500 newtons on the Earth. So the first question says, what is the weight on the Earth? The second part of the question says, what is the mass on both the moon and the Earth? And the mass should be the same no matter what. All right. And last but not least is number 12. So it gives us some information about a module in which astronauts are taking off from the moon. They're going to go up in a giant crane. They're going to take off, which means that their rocket has some thrust. The thrust of our engines is going to point opposite of the gravitational pull. So in other words, if gravity pulls us downward, remember we call that weight, then the amount of what we would call a thrust force must point opposite of that gravitational force. And in this case, it says it's 3,000 newtons. You're also told that the mass is 10,000 kilograms. Okay. Next thing says to calculate the magnitude of acceleration in a vertical takeoff. In other words, again for part A, F will equal m times A. We don't know A. Do we know mass? Yes, we do. Can we figure out F net given all of this information? Yes, we can. In order to do it, we're going to have to calculate mass times gravity because, again, they are... Oh, never mind. They're not taking off. They're taking off from the moon. So, again, weight equals mass times the gravity of the moon, which in this particular case is going to be the 10,000 kilograms times the 1/6 from the previous problem, so 1.635 mass meters per second squared. So our weight, 10,000 times 1.635 is 16350 newtons. If our thrust, so in this case we need to know what our F net is. So we're going to do our thrust force, which is pointing up, minus our weight force, which is pointing down, which we just calculated. Remember, again, it's up minus down. In this case, the overall motion has to be up. We're not trying to go back down to the moon's surface. So our F net is going to be 30,000 minus the 16,350, and we get 13650 newtons. From there, we're going to use that number. To calculate A, because again, the mass is the same. In this particular case, we're going to get 13,650 divided by 10,000 equals this. And that's our part A. All right. Part B says, would it take off from Earth? Okay, so in order to figure out whether or not this could actually happen, we're going to go back to our free body diagram up here, and we're going to see that our thrust force, which is opposing gravity, is going to be the 30,000 newtons. The weight force on the Earth would be m times 9.8. Okay, so in this particular case, weight would equal the 10,000 kilograms times the 9.81 meters per second squared on Earth. That would give us a force of 98,100 newtons. The F net then would be the 30,000 newton thrust minus the 98,100 newtons of weight, and that would leave us with a negative value of F net. If that's the case, then A would come out to be negative. And if A is negative, then A is going downward at a rate of 6.81 meters per second squared. In our particular case, acceleration has to be positive in order to have the rocket speed up fast enough to leave the atmosphere. And so in this particular case, the rocket's not speeding up, it's slowing down. So this would not be able to even escape the Earth's gravity at this point. In order for that to happen, whatever this weight force was would have to be lower than the magnitude of the thrust force. Okay? All right, so that's the end of those 3 problems. Like I said, if you have questions over anything that comes before number 9, it's going to be best to try to seek me out or just to check the answer key that's going to get posted. All right, have a great day.